Namaskar, I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Raj University, Kolhapur. Today I will discuss the separable extension from the normal extension and separable extension topic. And next point, second important point, main point is separable extensions from the field theory of MSC second semester 4. Definition of separable extension. Now see here. An irreducible polynomial f of x belongs to f of x is called a separable polynomial if all its roots are simple. Any polynomial f of x belongs to f of x is called separable if all its roots, irreducible factors, are separable. A polynomial that is not separable is called inseparable. This is separable polynomial, definition of separable polynomial. Now see here separable extension. Let E be an extensions of a field F. Let E be an extensions of a field F. An element alpha belongs to E that is algebraic over F is called separable over F if its minimal polynomial over F is separable. If its minimal polynomial over F is separable. Now algebraic extension definitions. And algebraic extension E of a field F is called a separable extension if each element of E is separable over F. Note that any polynomial over a field of characteristic 0 is separable. Thus, if F is a field of characteristic 0, then any algebraic extensions of F is separable. This is we know that irreducible polynomial over finite field have distinct roots. Hence, any algebraic extensions of a finite field is separable. We know that if k is equal to f of x be the field of rational function in one variable x over a field f of characteristic 3, then the polynomial y cube minus x in the polynomial ring k of y over k is irreducible over k. Also y cube minus x has all its roots equal, each being alpha same. Hence k of alpha is not a separable extension of k. K of alpha is not a separable extension of k. Definition. A field F is called perfect. Field F is called perfect if each of its algebraic extension is separable. If each of its algebraic extension is separable. Note, field of characteristic 0 and finite field are perfect fields. Infinite field of characteristic p greater than 0 have irreducible extension. Thus, such fields are not in general perfect. Now one more definition. An extension E of a field here is called sem4 if E is equal to f of alpha for some alpha belongs to E. Theorem. If E is a finite separable extensions of a field here, then E is a simple extension of here. If now see here proof. If F is a finite field, then by corollary, each finite extension of F is simple. So suppose that F is infinite. Since E is a finite extension of F, E is equal to f of a1, a2 dot 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 an, where an belongs to E, are algebraic over. We know that if E is equal to f of alpha beta, then there exists an element theta belongs to E such that E is equal to f of theta. Then the result will follow by induction. Let P of x and Q of x be the minimal polynomials of for alpha and beta respectively over F. Let the roots of P of x be alpha is equal to alpha 1, alpha 2 dot dot alpha n, and let those of Q of x be beta is equal to beta 1, beta 2 dot dot beta n. Since E is a separable extensions of F, all alpha I 1 less equal I less equal n, and all beta j 1 less equal j less equal m are distinct. Since F is infinite, there exists A belongs to F such that A is not equal to alpha I minus alpha divides beta minus beta j for 1 less equal I less equal n, 2 less equal j less equal to n. Then A into beta minus beta j is not equal to alpha I minus alpha. So A beta plus alpha is not equal to alpha I plus alpha beta j, A beta j. For j is not equal to 1, set theta is equal to A beta plus alpha, then theta minus I beta is beta j is not equal to alpha j for all 1 less equal I less equal n and 2 less equal j less equal m. Define h of x is equal to p of theta minus ax belongs to f of theta of x. Then h of beta is equal to p of alpha is equal to 0, and h of beta j is equal to p of theta minus a beta j is not equal to 0 for j is not equal to 1. So beta is roots of h of x, but no beta j is not equal to 1 is a root of h of x. Also beta is a root of f of q of x. Regard q of x belongs to f of theta of x. Let a of x belongs to f of theta of x be the minimal polynomial of beta over f of theta. Therefore a of x divide h of x and a of x divide a q of x. Then any root of a of x is a root of q of x as well as a root of h of x. But the only common root of q of x and h of x is beta. Therefore a of x is equal to x minus beta. This implies that beta belongs to f of theta. Then since theta is equal to a beta plus alpha, alpha belongs to f of theta, hence f of alpha beta is equal to f of theta, which is